Hey, I'm Yuval, and I will talk about a joint work with Vitaly Feldman, PAC learning with stable and private predictions. So we discussed two notions, stability and privacy, and their motivation is different, but they have very similar algorithms. And first, for stability with respect to the training set, and this is a well-studied notion because it implies generalization. And in this work, we want to understand how stable we can make our learning algorithms to be. And now I will discuss private prediction. But first, I want to present the standard model for private learning. And this is different from the model that we use here. And in the standard model, we assume that the training set contains private users' data, and there is a trusted server that learns the model from this data. And additionally, there is an adversary that has access to the complete model, and we want to ensure that no user information is leaked from this model. But in many cases, it's impossible to ensure privacy in these general settings. And for this reason, Dwork and Feldman and Vitaly, Dagan and Takuta suggested the private prediction model, which is the same model that we use here. And there, we assume that the adversary can only ask for a few adversarial predictions, but it doesn't have a complete access to the model. And we want to ensure that these predictions don't leak any private information. So this work has two main results. First, we show how to get stability for free with nearly optimal sample size. And secondly, we show improved algorithms for private prediction. And let me start by discussing the standard learning setting. There is a domain X and binary labels. There is a hypothesis class H with VC dimension D, a training set S that is drawn IAD from some distribution D, and we denote the learned classifier by AS, and it has randomized outputs. And this randomization is necessary for stability and privacy. And in terms of the loss, we use the expected 0-1 loss, where the expectation is both over a random input and over the randomness of the classifier. And we define the excess loss of the algorithm as a difference between its own loss and the loss of the best hypothesis from the class. And we denote the excess loss by alpha. And next, we define stable and private prediction algorithms. So we say that an algorithm is gamma uniformly stable if any change of one training sample changes any prediction probability by at most an additive factor of gamma. And formally, for any two training sets S and S prime that differ on one element, for any X and any Y, the probability to predict Y given X with the training set S and the probability with S prime, these probabilities differ by at most an additive factor of gamma. So that's for stability. And a private prediction algorithm is defined similarly, but now we want the multiplicative ratio between the two predictions to be bounded by e to the epsilon. And this is stronger than stability, so it's harder to achieve privacy in general. And our goal is to construct algorithms with a low excess error that are also stable or private. In prior work, Shalev, Schwartz et al. Provided a stable algorithm that split the training set into different partitions, as you can see on the right. It learns a single classifier from each partition, and then it outputs a mixture of the classifiers. Now, this algorithm will automatically be stable because each example can affect only one of the trained classifiers, and each of these classifiers has a limited influence over the final output. But this technique essentially increases the training size by 1 over gamma, because we have to train 1 over gamma different classifiers. And let's move to private prediction. And here, Dwork and Feldman gave a similar solution, but they added additional privacy mechanisms to ensure privacy. And it still remained open if there is a better way to enforce uniform stability or private prediction than splitting the data. So in the main result on stable prediction, we show that the sample complexity is approximately d over alpha squared plus d over gamma alpha, where alpha is the excess error, gamma is the stability parameter, and d is the VT dimension. And this means that we can get a stability of gamma equals alpha without increasing the sample size with respect to non-stable algorithms. And for private prediction, we give two incomparable upper bounds. The first result improved over the prior work by a factor of alpha. It was proven independently by Nandi and Basili. And the second result is tight in terms of alpha and epsilon, but compared with the lower bound, it has an additional factor of d in the second term. And I remind you that epsilon is a privacy parameter. And now I move to discuss the algorithms and the proofs. And the stable algorithm is very simple, and it has two steps. First, we select a finite approximation to the hypothesis class, and then we run an algorithm that is specified to work on finite classes. And this algorithm is the exponential mechanism. It's a randomized algorithm that samples a classifier from a finite class, and it gives higher probability to classifiers that have lower training loss. Now, it's both stable and has low excess error, but the sample complexity depends on the size of the class, so we cannot execute it on the original class because this class can be infinite. And we select a subset H prime that approximates the original class H. And that's how the subset H prime is constructed. So H prime is based on a random subset T of the training set that contains a gamma fraction of the examples. And H prime is defined to contain one hypothesis for each possible way that H can classify the training subset T. And we can bound the size of H prime by Sauer-Shelach lemma, and this gives a bound on the sample complexity of the exponential mechanism. So we move to the proof, and first we prove stability. We can see that each training example can affect the prediction in two ways. First of all, it can affect the creation of the subset H prime, but only with probability gamma, because H prime depends only on a random gamma fraction of the training set. And secondly, this example affects the exponential mechanism, but it is gamma stable. So the total stability is 2 gamma. And now for the error bound. So first, we claim that H prime contains an alpha optimal classifier, and this follows from the standard fact that H prime is an alpha net of H. And second, the exponential mechanism returns a classifier that's alpha optimal with respect to H prime. So the final output is 2 alpha optimal with respect to H. And that's for the proof. And let's recap what happened. So first, we use a small subset of the training set to construct a finite approximation of H. And then we apply a learning algorithm for the finite case. Now, the first private algorithm will execute the stable algorithm that we just presented with stability epsilon times alpha, and then it flips the output with probability alpha. And this noise that we added by flipping turns stability into privacy. But we probably get a suboptimal algorithm because the stability parameter might be smaller than actually needed for privacy. Now for the second private algorithm. So it begins similarly to the stable algorithm, and it also combines other privacy mechanisms from prior work. But the proof doesn't follow from prior work. And you can read a short summary of the proof in our paper. So to summarize, we suggest a stable and private prediction algorithms that are better than partitioning the data. And the stable algorithm is tight, and it gives stability for free. And the open problems are first to find the true sample complexity of private prediction, and second, to find efficient stable or private algorithms whenever they exist. Thanks for listening.